Hello, I'm Matt Miller. I'm a fellow in the SEAS program at NC State University. SEAS stands for Data Enabled Science and Engineering of Atomic Structure. We're a group of materials scientists, statisticians, mathematicians, chemists, physicists, and others who collaborate on research problems having to do with materials at the atomic scale. In these two videos, I'm going to introduce you to the concept of Bayesian statistics. Bayesian statistics has gotten more popular over the past couple of decades as computing power has increased and allowed for it. It differs from the more traditional ways of thinking about statistics, which we call frequentist statistics. We'll get to those differences in a little bit. Let's start with an example to build some intuition. Suppose I have a six-sided die. I drill holes into the face with 4 pips and fill the holes with lead. I then paint over these holes to make the foreface indistinguishable from before. I've created a loaded die. Opposite from the foreface is the three-face. Let's say you want to know the probability of rolling a 3. Since you are an expert at rolling dice and you know that I've weighted the foreface, what would you guess the probability to be? How confident are you in your guess? Take 10 seconds to write down your answers. You probably picked a probability greater than 1/6 because the probability of rolling a 3 with a fair die is 1 out of 6, and the lead is weighing down the opposite side. How confident are you? Well, it should depend on the information you have. If you know the weight of the lead inserted into the die, you might change your guess up or down, but for now, let's just say we think the probability is somewhere between 1/6 and 1. So how do we find out what the true probability of rolling a 3 is? We conduct an experiment. We roll the die and record what number is face up. Then we do it again and again, and once we roll it enough times, we'll have a really good idea of the true probability of rolling a 3. Now, let's simulate this experiment. After 30 rolls, we have 18 3s and 12 not 3s. So the sample proportion for rolling a 3 is 18 over 30, or 0.6. This leads us to believe that a 3 should pop up about 60% of the time. But we've only rolled the die 30 times. How close to the truth are we? How uncertain are we? How can we quantify that uncertainty? This seems like a good time to talk about the difference between frequentist and Bayesian inference. Let's answer these questions from a frequentist perspective first. Think about these 30 rolls as 30 trials in one experiment. Frequentists say that if we theoretically repeated this experiment infinitely many times, we would find the true value of the parameter of interest, which is the probability of rolling a 3. But it's impossible to do anything infinitely many times, so we make a confidence interval instead. I want you to take 30 seconds and write down your definition of a 95% confidence interval. What did you say? Was it something about how confident you are in the result, or about the probability of the true proportion being in the interval? Both of these are very common misconceptions. The underlying issue is that using the word probability implies some randomness to the parameter. But from a frequentist perspective, the proportion has some true value, meaning there can't be any probability associated with it. It either is the value or it isn't. But the catch is we will never know what the true value actually is. Here's what a 95% confidence interval says. If I repeat my experiment infinitely many times, 95% of the confident intervals I make will contain the true value of the parameter. That's a hard concept to remember and understand, which is why scientists often get it wrong. Since we're simulating these data, even though we can't repeat this experiment infinitely many times, we can repeat it a lot. I've repeated it 100 times and created confidence intervals for each one. The blue line in the plot is the true value of the proportion, and the vertical lines are the confidence intervals for 100 experiments. You can see that 6 of these intervals don't contain the true value of the parameter, and 94 do. So about 95% of them contain the true proportion, which is the definition of a confidence interval. Also note that the first one, which was our first experiment, doesn't contain the true value. This is an important lesson. Remember, a confidence interval isn't a guarantee that you've captured the truth. The definition and interpretation of a confidence interval feels clunky to me. Sure, I believe there's a true value for the parameter, but we'll never know what it actually is. Can we at least pretend that there is some randomness and probability distribution associated with the parameter? We can. Treating parameters as random variables is the heart of Bayesian statistics. It lets us think of parameters the way we want to think of them, the way you may have written for your definition of a confidence interval. In our next video, we'll get into the mathematics of Bayesian statistics and continue with our loaded die example.